In this lecture we will see how one can handle in analysis the internal resistance of a non-ideal inductor or the internal conductance of a non-ideal capacitor. The motivation for doing that is the following. In second or higher order RLC filter constructions, the inductor capacitor pair, okay, in general appears either in parallel, okay, that is of this topology, or series. Okay, like that connection. Now, since that's the case, an important, from a practical point of view, pair of questions are these, okay? What is the effect of the internal resistance of the inductor in the parallel connection, in the okay, and of course we have the dual question. Let's also put it down. The dual issue is the internal conductance of the capacitor in the series connection. Okay, what is the effect of the internal conductance of the capacitor in the series connection? Okay. Now consider the first question. That is, we have a parallel LC as part of our filter, but the inductor is not ideal. Okay. So therefore, it has to be modeled by a resistor that appears in series with the actual inductor. Okay. So we have the non-ideal parallel capacitor inductor connection. Okay. So this is the inductor. This is the internal resistance of the, well, this is the resistor that models the internal resistance of the inductor. Okay, and this is our capacitor. So this is the internal resistance of inductor. Okay, so let's call the equivalent impedance here Z1. Okay, now what we want is, in our filter constructions, we want the LC pair appear in parallel, but due to this non-zero resistance, they are no longer in parallel connection. Of course, if this is very, very tiny, then we can just ignore it and we would have the parallel connection. So that's an approximation, simply ignoring R. But if R is not that small but not that small, then it has to be represented somewhere else, if that's possible, okay? So what we want to figure out is whether it's possible to approximate this one port, okay, that connection, by another one port where L and C, they appear in purely parallel form, okay, and this resistance is thrown somewhere else. So this is the approximation. Validity of which we will now try to figure out. Okay, in our approximation we have a more pleasant topology where inductor and capacitor, they appear in parallel, and then the internal resistance of the inductor here is represented as a resistor outside this parallel connection, okay? So we have L, we have C, and here we have, let's call it R2. And this new, the impedance of this new one port or approximate one port, let's label or denote by Z2, okay? Now we will try to figure out under what conditions Z2 or this topology is a valid, is an acceptable approximation of the original configuration. Okay, so let's now try to figure out the value of R2 so that our approximation is a good one. Okay, to find R2, let's obtain Z1 and Z2 and compare them, and by choosing R2 in an appropriate way, let's try to make Z2 be close to Z1, okay, in some sense. Okay, so what's Z1? Z1 of S, the impedance, is 1 over the equivalent admittance, and equivalent admittance is admittance of this guy plus the admittance of the capacitor. Okay, the admittance of the capacitor is CS, okay, and the admittance of this is simply LS, 1 over LS plus R. LS plus little r. And that can be written as 1 over C times S plus R over L, S squared plus R over L, S plus 1 over LC. Okay, so that's our Z1. And now, how about Z2 of S? Z2 of S equals 1 over the equivalent admittance, and the equivalent admittance is sum of individual admittances, because all those three components appear in parallel. So we have 1 over the equivalent admittance, which is 1 over SL plus SC plus 1 over R2. And that equals 1 over C times S squared plus 1 over R2CS plus 1 over LC. And here we have S as the denominator. Now, what we want is we want to pick R2, choose R2, so that this thing Z2 is a valid or a good approximation of the first case, okay, of Z1. And for that, it seems reasonable to choose R2 so that the denominators become equal for Z1 and Z2. Note that by choosing just R2, we cannot make Z2 exactly equal Z1, okay? So that's, it's not possible to obtain exact equality, but let's try to make Z2 as close to Z1 as possible. And one way to do that seems to be to choose R2 so that they both have the same denominator, okay? So let's choose R2 equals L over R times C and plug it in here, and then what happens is Z2 of S becomes equal to 1 over C times S squared plus R over L S plus 1 over LC. Okay, so this is Z2 after our choice, and this is the original impedance Z1. Okay, note that they are not the same due to this term here, R over L, where in Z2 we don't have. Now here is an important observation. Let's put it down. Remark: if we adopt the notation S squared plus R over L S plus 1 over LC equals S squared plus 2 alpha omega 0 S plus omega 0 square. And let Q be 1 over 2 alpha, okay? And 1 over 2 alpha in terms of the circuit parameters is square root of L over R times square root of C. Then in terms of Q, R2 becomes Q squared times R. Okay, then R2 can be expressed in this new notation, Q squared times R, where R is the resistance representing the internal resistance of the inductor. Okay, now let's proceed to write down the impedances in terms of J omega. Okay, that is now their circuits. They're part of circuits, let's say, in sinusoidal steady state. Okay, so after our choice, R2 equals Q squared times little r, we have the following. Z1 J omega equals 1 over C J omega plus R over L divided by the denominator, omega squared plus J R omega over L. So that's our Z1. As for Z2, Z2 J omega, that equals 1 over C, just J omega, instead of that J omega plus R over L, 1 over LC minus omega 0, omega squared plus J R omega over L. Note that the denominators are the same because we chose R2 to make the denominators the same. Okay, now observe that when the frequency is around omega 0, namely is around 1 over square root of LC, we can write the following: Z1 J omega equals. So, okay, So around omega equals 1 over square root of LC, what happens is right. So we can ignore this part 1 over LC minus omega squared because it will cancel, and Z1 of g omega and Z2 g omega boils down to the following. Right. We have as for Z1 L over RC minus J square root of L over square root of C. Okay, so that's Z1 g omega, and as for Z2 g omega equals, okay, R2, which is L over RC. Okay, so Z1 g omega approximately equals that. Now, they're almost the same. Here, this is almost a real, purely real, and here we have some imaginary part. Okay, and we can say that both are equal to one another if this thing is small. The imaginary part is small compared to the real part. Okay, so if the real part is, the magnitude of the real part is much larger than the magnitude of the imaginary part, then this part can be ignored, and when it's ignored, what we have is Z1 and Z2 become approximately equal, and that means we can, that means our parallel approximation, where L, C, and resistor, they appear all in parallel, would be a nice approximation to the original one port, where we have an inductor connected in series with a resistor representing its internal resistance. Okay, note that Z2 j omega, namely our approximation, nearly equals Z1 g omega, provided that the real part of Z1 g omega is much larger than the imaginary part, magnitude-wise. Okay, much larger than square root of L over square root of C. Okay, so that allows us to make the following conclusion regarding our approximation. Here is the conclusion of our analysis. If this condition is satisfied, which can be written in the following form: if square root of L divided by R square root of C is much larger than unity, and remember our notation, this was what we defined as Q. Okay, if Q is much larger than unity, then provided that the operation frequency, or the operational frequency, the range of operation frequencies for our one port is around this frequency, omega equals 1 over square root of LC. Okay, around frequencies omega equals 1 over square root of LC. This circuit, non-parallel LC, one port, can be approximated, approximated by the following parallel RLC, LC, and this is L over RC, oops, okay, or Q squared times R, where Q is this thing. Okay. So that's how to move from this non-ideal parallel connection to the ideal parallel connection, where pure L and pure C, they appear in parallel. Okay, now let's very briefly talk about the implications of this for the dual case, and then we can finish our lecture. The dual case. If, okay, square root of C divided by G square root of L is much larger than 1, then around frequencies, okay, now I'm dualizing this conclusion, okay, if the dual of this is much larger than 1, then around frequencies omega equals 1 over square root of LC. Well, to be purely dual, let's make this CL. Okay, around frequencies CL. This thing, that is the dual of this circuit here, which is a capacitor connected in parallel with a conductor, and the whole thing is series to an inductor. C, L, and this is G. Okay, measured in moles. That's the internal conductance, or that is representing the internal conductance of our non-ideal capacitor. Okay, so this thing is internal conductance of our non-ideal capacitor. Okay, this connection can be approximated as the following circuit, where everything is in series. Okay, C, L, and this boils down to C over GL. C over GL, and its conductance. Okay, and this, well, while this here is resistance.